So I wanted to do one last short video where I try to put everything into perspective in case the narrative has gotten muddled at any point throughout the semester. So basic animating questions are, first of all, how does everything we learned connect? So hopefully all of the different topics we've covered don't just seem like disparate, islands that aren't really connected to each other, don't have any underlying unity. So I'd like to hopefully address that point, and also want to ask the question, why were all the various topics necessary? So I think it would be a shame if you thought any particular topic was just a result of me wanting to bug you with some vacuous intellectual exercise. So basically, these are my goals for the lectures, to address these two questions. And hopefully I can do this without going on too long. So it's probably a good idea to just sort of remind ourselves, and I think I said this in the beginning of the semester, but just to kind of put this whole subject into perspective, sort of why are we studying analysis? And the reason we're studying analysis is basically for the same reason that it was invented historically, which is to give a solid foundation to calculus, which we know is one of the major revolutions in human understanding of the natural world. It came out of the mathematical apparatus of calculus, what was called the differential calculus and the integral calculus. So we like to give this a solid foundation, and the reason for that, calculus was doing just fine explaining the natural world for a while, but why bother with this, this rigorous foundation for calculus is that calculus got to a point where there was sort of a various crises of understanding. So the foundations of calculus that were improvised by Newton and Leibniz eventually kind of became insufficient. They couldn't bear the weight of all of the developments that were laid on top of it, and so some misunderstandings had been accumulating, and so the edifice was starting to teeter noticeably, and so that had to be addressed by the mathematicians. So how was it then that understanding central calculus concepts like what continuous functions are or what the derivative is, how did that lead to these funny, abstruse, abstract concepts that we discuss in the class, like, for example, the completeness axioms for the reals, or the notion of a compact set, or the notion of a subsequence, and etc. And so we have all these kind of arcane terms. They don't seem to really have all that much to do with the derivative of a function. So how did studying things like the derivative lead to these crazy things? And I think maybe the best way to try to illustrate how this came about is to do a case study. So I want to look at just one theorem in particular, and that's the mean value theorem. So we know what the mean value theorem says. We just covered it recently. It says that the average value, the average rate of change of a function over the interval from a to b is equal to the instantaneous rate of change of the function at some point in between. Okay, so illustrated by this figure, the slope of this line is realized by the slope of the tangent line at some point in between. That's the mean value theorem. And this is actually a theorem that Cauchy had to figure out how to prove in sometime in the 1800s when he was working on the foundations of calculus. Essentially, Cauchy was responsible for many of the developments in this subject. The epsilon delta definitions of continuity, for example, is as far as I know, due to him. Okay, so try to put yourself in the mindset of Cauchy, trying to prove the mean value theorem. Okay, so we have this sort of intuitive statement about the derivative here, and we want to figure out how to prove it. So try to inhabit his mindset to understand what I'm trying to do here. Okay, so the mean value theorem is this general statement, and if we're trying to figure out how to prove this general statement, two plausible things could happen. You could either see that the mean value theorem reduces to the special case, which is known as Rolle's theorem, or you could imagine just investigating the special case that's encapsulated by Rolle's theorem. And so you're trying to prove this general mean value theorem. It might make sense to try to simplify things and look at the special case that's discussed in Rolle's theorem, where the value of the function at the endpoints are equal. So your average rate of change is 0, and therefore you're trying to find a place where the derivative is equal to 0. We saw in the proof of the mean value theorem that, in fact, Rolle's theorem implies the mean value theorem. So this special case really doesn't have any less power than the original. So either you see these two things are equivalent, or you're just sort of investigate the special case. So those would be kind of natural developments if you were thinking about the mean value theorem. You would eventually at some point come across Rolle's theorem, have to prove Rolle's theorem. Okay, so let's think about Rolle's theorem. So how do we prove Rolle's theorem? We've now kind of reduced the mean value theorem to thinking about Rolle's theorem. How do we prove this? We're trying to find a place where the derivative is equal to 0 in this situation here. Well, anybody investigating the foundations of calculus will be well versed with the methods of calculus, and so they would know that the derivative is equal to 0 at any local max or local min by Fermat's principle. And so it would be a natural idea while investigating Rolle's theorem to think about the interior extremum principle of Fermat. So in order to locate a point where the derivative is equal to 0, all I have to do is locate a local max or local min of this function here. Okay, so in order to do that, well, all I have to do is be assured that that such a local max or local min is going to occur. And so it makes sense to just look for the global max or global min of your function on this interval from a to b. And so therefore we kind of have this pair that Rolle's theorem is going to be implied by the interior extremum principle here and the extreme value theorem, right? So if we have an extremum of our function, then we'll just look at the derivative there. As long as that extremum occurs in the interior, the derivative will be 0. So we're led to thinking about the extreme value theorem. Fermat's principle is a relatively simple thing, doesn't require anything particularly complicated, but the extreme value theorem is where the real action is at. So what we have here is a continuous function defined on this closed and bounded interval from a to b, and we're sort of imagining the image of this interval under a continuous function, and it's going to be, we now know from our work in this course, right, it's got to be a connected and compact set, so it's going to be some interval. And the maximum is going to be the right endpoint of this interval, and the minimum is the left endpoint of this interval. And we know from our work in this course that some point in this interval has to, some point or points in this interval have to map to that maximum, and at least something has to map to the minimum. But again, try to imagine that you're Cauchy, okay, or someone like him, right, before all the fancy things that we discussed in this course. If you were thinking about a continuous function on a closed and bounded interval like this, how would you actually go about proving that it has a max and a min? Okay, so you got to try to inhabit this state of mind. So far we haven't really left the realm of thinking about continuity and differentiability. But the extreme value theorem is where things kind of take a turn. Okay, so thinking about this question, so why does a continuous function on this closed and bounded interval have a maximum? Well, there's sort of two components to this. So first of all, we would want to know that the image is bounded, and then if it was bounded, we would have to show that it actually has a maximum point and a minimum point. So I'm just going to think about the question about whether it's bounded. So that'll be sufficient to illustrate my point. So, okay, so we want to. So our natural step is we want to show that this continuous function, the image of this interval, is bounded. Okay, let's say we're trying to show that it's bounded from above. So suppose it's not bounded from above, right? It'd be kind of natural. You have to produce a bound on the image. How are you going to do this? You just have a kind of general continuous function and interval. Well, it's simplest to assume that it's not bounded and kind of see what goes wrong. Okay, so you would have a mental picture kind of like this. You have points x1, x2, x3, etc. And those points, their images are mapping further and further to the right, further, closer and closer to infinity. So you got x1, x2, x3, x4, x5, x6, and x7, etc., going further and further out, closer and closer to infinity, quote unquote. And so you can kind of imagine, to write this condition down, you have all these points x sub n in this interval, and their values are bigger than or equal to n. Okay, so marching along towards infinity. And then you'd have to ask yourself, again, we're inhabiting the mind of a mathematician of a couple hundred years ago, so you have to ask yourself, well, why is this a problem? What's the issue with this? And if you believe that this function should have a maximum, there should be some kind of problem here. And you'd probably want to realize, thinking about sort of other situations, thinking about various examples, that this situation, it's not a problem, say, for a simple function like 1 over x on the interval from 0 to 1. Right, because you just have the sequence of points 1 over n approaching 0, and the value of the function at 1 over n is n, right? So you have this sequence xn where the value of the function is greater than or equal to n. And that's not a problem at all on this interval, right? This is a perfectly nice continuous function, or you can sort of draw a reasonable picture. The graph is unbroken, so that looks perfectly fine. This is a finite interval. So we have this situation where we have this finite interval and this continuous function, but it's not bounded in this way. But we do believe that it should be bounded if we have a closed interval. So what's kind of the difference here? And this is where we get kind of a cascade of concepts. So the problem arises because we have this sequence, and it's in a certain type of set, right? So we notice that the set matters, the underlying set here. We're in a closed and bounded interval, right? So if you change that closedness, if you remove one point from the interval, then all of a sudden you can find continuous functions that aren't bounded. But we have this sequence in a very certain kind of set. It's closed and bounded. And once we have that, the closed and bounded, we know from this course, from our work, and this probably, this would have to be arrived at by our mathematician of old, but they would have to realize that this sequence kind of might dance around in this set here, kind of moving back and forth, but there's going to be a subsequence of that sequence which converges to some point. And it's going to converge to some point in the set itself. So in this case here, right, in this sort of counterexample, if you change the interval a little bit, you have convergence of your sequence, but it's converging to something that's not in the set, right? It's converging to, these 1 over n's are converging to 0. So they would have to realize that what's going on is you have this sequence, you have a very particular type of set, and in this type of set, you're going to be able to extract a sequence from your sequence, right? You extract a subsequence, which is converging to some point. Okay, so sort of these points of your sequence are clustering around some certain point. And remember, so what allows us to extract this convergent subsequence comes from a characterization of compactness, right? One of our characterizations of compactness is that there's a subsequence of any sequence which converges in the set. And so essentially what our mathematician would be discovering is a characterization of this closed and bounded interval. It's discovering something about the compactness of this closed and bounded interval in terms of sequences and subsequences. And this is essentially equivalent to the Bolzano-Weierstrass theorem. Right? Bolzano-Weierstrass saying that any bounded sequence has a convergent subsequence. And so here we have this sequence coming out of this bounded set. So once our mathematician's able to extract this subsequence, which is converging to this point in the set, right? And so the closedness would guarantee that our limit point is in the set. Then comes the continuity, right? Since this sequence is converging here, the values of the function on the sequence have to be converging to the value of the function at x. And so this is where our mathematician would discover the problem. If we have this sequence of function values going off to infinity, then the value of the function itself at x would have to be bigger than or equal to any natural number, and that would be a contradiction. And to make this step, really what's going on is, well, we have to know something about continuity, right? This is getting to the nature of continuity, that our continuous function sort of preserves this convergence. When we have convergence here in the domain, we have convergence in the image like this. And there's also something about this, right? We sort of have an order limit theorem thing going on here to conclude that f of x is bigger than or equal to n. Each of the x sub n's, right, they're going to be bigger than these natural numbers, so the f of x is going to have to be greater than or equal to all the natural numbers as well. Okay, so there's acquaintance with the definition and properties of continuous functions going on here to make this final step. Okay, so the last step uses essential facts about continuity. And going back here a little bit to this Bolzano-Weierstrass, note that the Bolzano-Weierstrass theorem is really its equivalent to the completeness axiom of the reals. Bolzano-Weierstrass is kind of one way to say that the reals don't have holes in it. There's no holes in the reals. So when you get back to the point where you're talking about Bolzano-Weierstrass theorem, you're really talking about the nature of the real numbers themselves. So what we find here is that to prove the mean value theorem, we're working backwards really until we hit bedrock in the subject, and that we're asking ourselves fundamental questions about the nature of the reals themselves. The Bolzano-Weierstrass theorem doesn't hold for the rationals, for example. You can have a bounded sequence of rationals, like just take the decimal, better and better decimal approximations to the square root of 2, for example. That would be a bounded sequence of rationals which does not converge in the rationals. You have to leave the rationals to talk about the convergence of that sequence. But that's not something you have to do for the reals. Whenever you have a bounded sequence of real numbers, they're always going to converge to, or have a subsequence which converges to a real number. So we're really getting down to, to fundamentals of what the real numbers are when we're talking about the Bolzano-Weierstrass theorem. Okay, so you see our progression here. We were just talking about differentiability, then we were kind of talking about continuity, and asking questions about continuous functions, and then that leads to sequences, to thinking about certain types of subsets of the reals, right? So this is your topology coming in, the closed and bounded subsets. So we have to know something about how sequences interact with these types of subsets, right? So we have theorems about theorems relating compactness to the notion of sequence and subsequences, and questions about those subsequences, leading us to the nature of the real numbers themselves. And then we also have continuity and how continuity ties in with sequences and having to understand the nature of continuity. Okay, so we, just looking at the mean value theorem here, we kind of move backwards through all of the topics that we covered sequentially in the course, right? We have continuity, back to topology, and sequences, and then the real numbers. So we ran all of this forward throughout the course, but you can see how they kind of come about naturally by working backwards from an important result like the mean value theorem. And so that's basically what I wanted to emphasize in summary, and the point of all of this is to say that there's a unity and necessity to all of the material that we've covered. So all of these concepts tie together in an organic way, right? So just looking at this one result, you see how all of these things, one thing sort of leads back to a previous more fundamental thing until you get all the way back to just asking questions about the real numbers. So having to really dig into what it means to talk about the real numbers. What is their nature? And there's also a necessity, right? So this case study, right, we're talking about a very important theorem, the mean value theorem. So if we want to understand important theorems about the derivative, like the mean value theorem, it's necessary to understand how to prove it. And so therefore we need all of these concepts, right? Sort of all of these concepts are lurking behind the scenes and begin to reveal themselves when we start asking these kinds of questions. All right, so that's going to do it for the video and the semester. I hope it's giving you reasonable perspective on what we've talked about in this course, and I hope you've enjoyed the journey.